Welcome back, everyone, and glad that you joined here. So after introducing the algorithm of Oculus, we now move on to another one or to a different one, namely 4C, which stands for Computing Correlation Connected Clusters. And the idea here of 4C is actually to combine the concepts from PCA in a local context where this locality is captured through applying density-based clustering in a modified sense, in a modified version. So density-based clustering, as you may know from the clustering algorithm of DB-scan, something like core point, density connected, density reachable, and all of these properties, they are incorporated into this work of 4C. So the general approach is to check the core point property of an object P, this red one here, for instance, in the complete feature space that we have in the beginning. Then, after having like this local neighborhood, because we say this, we look at this object within a certain neighborhood, there we apply on this set of this of the object P with its neighborhood PCA, and this is the local part. So we apply PCA on the local neighborhood S of this point P that we have here to find subspace correlations. And what we have here is, again, as a recap, the factorization which PCA comes with. So it factorizes a matrix MP, which is the covariance matrix, into three components, V, E, and V transpose, where V, or V transposed, denotes the eigenvectors resembled in the matrix, and the matrix E resembles the eigenvalues. 4C comes with a parameter delta, which discerns large from small eigenvalues, so you can consider it as some sort of like a separator. So to speak, the correlation dimensionality of a local neighborhood. So if we look here at a local neighborhood here around this object P, this is something which should have number of eigenvalues which is greater than delta. If it's greater than delta, then we have like the definition of our correlation dimensionality of this neighborhood. In the eigenvalue matrix, so E that we have, we perform a modification, and we shall see within the next slides what these modifications are actually good for. So the eigenvalue matrix of this object P with its local neighborhood S, the large eigenvalues that we have, they are replaced by 1, while the small eigenvalues in there, they are replaced by a value kappa. This is K-ish letter is a kappa, which is set far greater than 1. So what we have here is actually an adapted eigenvalue matrix E prime index P. I may think, what is this kappa thingy actually good for? Well, by setting a high kappa value, it comes close to that we penalize or higher weight deviations from that correlation subspace. And this has also impacts on this epsilon range, or this neighborhood for where we are looking for densely connected areas. Because if you recall, for instance, DB-scan, density-based clustering, you have around an object a circular or spherical or hyperspherical epsilon neighborhood. And in this context of 4C, this circular or spherical neighborhood changes to an ellipsoid one. So it's like you have this and you squeeze it down to an ellipsoid. And this gets probably more clear on that slide. So the effect on the distance measure by modifying the eigenvalue matrix is that we have here, this is, let's say this axis denotes epsilon, and this axis here is now epsilon divided by kappa. So that's the effect if we modify those entries with small eigenvalues to a value which is far greater than 1. What happens if kappa gets larger? Then the whole expression here, epsilon divided by kappa, gets smaller. This means the higher we choose kappa, the more we keep squeezing this epsilon range. So that's the effect of a larger kappa. And this means that we are more tolerant in this direction. So we say we take here still this epsilon, but as soon as something deviates in the direction orthogonal to this principal component, then we are no longer considering it as within the epsilon range. Because in dbScan, we say within a given epsilon range, we have at least min-point objects. And if that is the case, then this red object P is considered as a core point. But imagine we would have here also other green objects around it, and we would squeeze that further, then we would, in certain conditions, have lower or less number of objects within this radius than expected. So kappa serves the purpose of actually squeezing that epsilon range in a specific direction, forming this ellipsoid, and by that obtaining then this particular correlation, directional correlation distance. If we look now at the distance function, so given now two objects, this time P and Q, both objects are any objects, they are not necessarily any centroids like in local PCA or Oculus, then the distance between P and Q is P minus Q times Vp times E prime P times Vt, V transposed P, Vp transposed times P minus Q transpose. So this is the one direction. However, in this case, we do not have the symmetry property, because since we do not have a unique epsilon range in all directions, but in two different directions, we have two different ranges or radii, we no longer can handle with or maintain the symmetry property. One may be like this, another one may be like that. So how do we handle that circumstance? By the way, you see again, this part, except this square root, is some kind of similar to the distance function we had in local PCA. So we have this part and this part transposed, and we have here this triplet, which is then something like, if you multiply it, would yield a modified covariance matrix. Because as we said, the covariance matrix M is a decomposition into V, E, and V transposed. And here we have now this modified E prime. So the symmetry of distance measure, how do we obtain it? As mentioned, we have here P and Q. So the distance from P to Q may be different than the distance from Q to P. So they may have different results that are going to be yielded. And the question is, how do we actually compute now the distance? We have a distance between P and Q and P. How can we somehow maintain some kind of symmetry? And we say P and Q2 objects are correlation neighbors if the maximum, so the distance between P and Q and the distance between Q and P, if the maximum from these two is still smaller than the epsilon range that we have here. If that is the case, so if you recall, this one axis is the epsilon radii, and the orthogonal to it is the epsilon divided by kappa. So we say if this the maximum from these two is smaller or at maximum equal to this epsilon parameter that we set, then the P and Q can be considered as neighbors, correlation neighbors. Then regarding the results, because what are the implications of this correlation neighborhood and of this modified eigenvalue matrix and so on? If we apply on this two-dimensional data set dbScan, then it would detect this whole entire reddish stuff, except the outliers, the noise points here, as one big cluster. If we apply now 4C on it, then it will recognize this as one cluster and this as one cluster. So we see the differences here. What happens if we apply a density-based clustering algorithm, which is tailored at detecting corresponding subspaces, versus a full dimensional density-based algorithm with these dashed lines indicated like dbScan. And on the other hand, we have like 4C versus Oculus, since we had Oculus beforehand. 4C in such a data set would recognize here one line, and here one line. Oculus may detect different things, and this is also one aspect of the instability. It may detect this one particular cluster and here one cluster. It may detect this one and this one and this one. It may detect this one here in the middle that you see. So it does not seem to capture that well the single clusters as good as we have it here. And I bet 4C may also be capable to detect this larger blob, if we modify correspondingly the parameters. So what are the properties of the 4C algorithm? First, it finds arbitrary number of clusters. So we no longer have this limitation or advantage, depends how you look at it, of stating that we want to have exactly k clusters, but you say, I don't know how many clusters, just find them for me. Then it requires user-specific density thresholds. So like in dbScan, you have to specify a minimum number of objects. You say, I want to have within a given epsilon neighborhood, but you also have to provide at least mu objects. While minimum number of points is kind of intuitive, it is hard to guess the epsilon range. And also mu and epsilon hold for all clusters that are potentially detected. So you do not have any cluster specific where you say, for that region of the data set or for that cluster, I want to have a different minimum min points and epsilon range. These two are global parameters again. And it is biased to a maximum dimensionality of correlation clusters. This is user specified. So with the parameter lambda, you say, I want to have at maximum lambda equals 2-dimensional clusters. And we have this parameter delta, which mediates the tightness of the detected clusters. So you kind of have a control mechanism of how much deviation from a subspace you tolerate. If you set, for instance, a higher delta, then you say, okay, the clusters may be a bit coarser, less fine correlated. And if you say, I want to have a smaller delta, then you force the clusters to be dense around a specific line or hyperplane. And we have this parameter kappa, which contributes to this thickness, similar to delta, and thus to the permitted deviation from the subspace clusters. So as we've seen, increasing kappa increases the penalty for distancing away, because the second direction that we had is like epsilon divided by kappa. And if we increase kappa, it's like we say this one dimension gets smaller and smaller and smaller in that particular direction. And if we choose a larger kappa, we say, no, we do not permit that much deviation in this orthogonal direction. It is has an instance-based locality assumption, meaning that correlation distance measure that is specifying the subspace is learned from the local neighborhood, from this neighborhood of this object P per instance of each point in the entire d-dimensional or full-dimensional space. It is a local correlation clustering algorithm. So what does it mean? Suppose we have one cluster here and one cluster here, and they are a bit apart. 4C is not going to say that these two are the same, although they have the same rotation and they have the same translation to origin or distance to origin. They will not be considered as one cluster. Although if you project this one and this one to its orthogonal cluster subspace, they would both of them fully overlap almost. So this is one issue. It is a local correlation, or not an issue, but a property as a local correlation clustering algorithm. In contrast to Oculus, and this is what I mean with the contrastive view, it can detect outliers. Since it is based on the density-based criterion from dbScan, it is capable to distinguish between noise points, which are neither a core point nor density reachable, versus objects which are either core points or that are somehow like density connected or density reachable. The enhancements are also based, there are enhancements of this version of 4C, which are also based on PCA, like 4C. The one is COPAC, which, as far as I recall, relies not on the epsilon range as for the neighborhood, but the KNN range, or KNN, K nearest neighbor distance of the neighborhood. And also ERIC, which is like a hierarchical variance. So it detects not only dense regions in subspaces, but detects like dense regions that are located on a line. This line, linear correlation, is located on a plane, and this plane is located in a hypercube, and so on and so forth, or cuboid. So there are several variants of it, Coparc, Eric, Heiko, which are inheriting properties, core properties from 4C. What is also interesting in this context, we said that the dimensionality in local PCA and ORCLUS is fixed. So if you say you're looking for L-dimensional or M-dimensional subspace clusters, then all of them will be of that dimensionality. Here in 4C, we have an upper bound. So we say at maximum, the clusters should have at max lambda dimensional subspace. However, they may be different. So they may be one cluster which is one dimensional, another cluster which is two dimensional, as long as lambda is not reached. So here we have indeed an assignment, potential assignment of individual cluster dimensionality, since lambda is an upper bound. The so far proposed techniques, local PCA, ORCLUS, 4C, and also Coparc, Eric, Heiko, and so on and so forth, they all rely on principal component analysis on PCA. It is a mature technique which permits the construction of a broad range of similarity measures, as you've seen by modifying, for instance, the eigenvalue matrix for local correlation of attributes. However, this is one major drawback. All of these PCA-based approaches suffer from locality assumption. So successfully deploying PCA in correlation clustering in really high dimensional data, like several hundreds, thousands, 10,000s, millions of dimensions, requires more effort. So how can we overcome this nasty locality assumption, you may ask? We need a different method to determine the correlation. This would be one way. Or we look for something else besides PCA. And there are indeed some approaches like, because besides of PCA, there's something like ICA, independent component analysis, on which algorithms like ISAC or SONAR rely on, as you've seen in this one big overview, which we're not dealing here with, but you can ask me, feel free. And another one, which is my personal favorite, is the so-called Huff transform, originating from computer graphics, which was originally designed in mind to detect structures like lines and circles on images. So cache is going to come up. Cache is a bottom-up arbitrary oriented subspace clustering algorithm. However, this is just a teaser, and stay tuned for the next video about the cache algorithm.